Okay, back again, guys. So we're still looking at refrigeration. So this is an example, right? So here on this refrigerator, they said and a vapor, okay, a vapor compression refrigerator make use of a methane chlorine. Okay, make use of methane chlorine and has a pressure limited to or limited of 177 kilopascal and 967 kilopascal respectively. And then so that means this is your pressure number 1, and then this is your pressure number 2. And then they said at the commencement of compression, the methane chlorine, your methane chlorine, it's your refrigeration agent. And then they said it's dry saturated, and after compression, the temperature is 102 degrees Celsius. The compression now, they said okay, the compression has a cylinder diameter and a stroke length of this one. So this is your compressor. So the compressor has a diameter and a stroke length of 75 millimeters. So the revolutions of the compression is 300 per minute with a volumetric efficiency of 80%. Then we also have the temperature of the liquid refrigerant leaving the condenser at 35. And then we also have another one, which is at the specific heat capacity is this one. And then they say now we need to calculate the coefficient of performance, the mass of the flow, and also we're also calculating the the refrigerating water required. Okay, so here we have to name our our pressures now. So from here we're going to deal with the scale. Okay, let's put our this is our volume. Okay, if we need to simplify, we need to put the values on these diagrams or our graphs. So here we have a pressure of 177. Let's also zoom it out. Okay, so we have a pressure of 177, and then we also have a pressure of 967. Okay, and then here we are given the temperature. Here they said we have the temperature of this one is the temperature of the condenser. So this is the temperature of the liquid refrigerant leaving the condenser. So leaving the condenser is what is our number 5. So this one is going to be your 35 here. And you also have the other one, which is this temperature. Here they said at this point, at the commencement of the compression, the methane chlorine is dry saturated, and after compression so after compression the temperature is this one, which is 102. So this is said this is our compression here. So from this point to this one is our compression. So after compression, this is your 102 degrees Celsius and also 32, right? So then we are also given this table here of our values. So most of the cases, if you have such question, you will be given the table. Okay, so when looking at the table here, we have the pressure of 177. The pressure of 177 has sorry, let's go back a bit. Okay, the pressure of 177 has a temperature of 10. So this is our initial. So that means our initial temperature here is 10 degrees Celsius. And also our pressure number 2 has a temperature of 45. So that means this one is our 45 degree Celsius. So from to pressure number 2. So remember we said from this point to this one is the compression, which is the external energy. The external energy that we added from this point to this one, and then from here we move at a constant pressure from 3, 4, 5. So that's why we have here at 3 and 4 the pressure here is still at 967, which is 45 degrees. And then we have the pressure number 1, the initial one is this one, and then this it's we said from here this is our point of number 2 to this one is the condenser, and then from here to this side is your throttling valve. So this is the one that it's leaving the condenser. This is the under refrigeration agent. It's the under refrigeration. So if it's under refrigeration, it's dropping all the heat energy because of what? Because of the condenser. So the condenser dilutes what your steam into liquid. So when that process happens, that means your liquid or your agent, it loses heat energy, right? And then now to calculate our values, we'll be looking at the table mostly, and also our to come. Let's look at our table here. Okay. Okay, yeah, we have a space. Okay, so then now to calculate the following, we should say we need to calculate the coefficient of performance. We should say the coefficient of performances will be H1 minus H number 6 over H2 minus H1. So then now we need to find the values of H1 and H2. Okay, sorry for that disturbance. Okay, so here we need to calculate our H number 2 and 1 and also H number 3. So now remember we said to get our H number 2, to get H2 or H number 3 is going to be okay. So then now to calculate the values of H2 and H1. So to get the value of H2, your H2 will be equals to H number 3 plus Cp into H number 3 minus H number 2, T number 2, like this. So then when you're looking at your enthalpy, let's go to this one of enthalpy. So here is what is happening here. We said number 2 is the external one. It's the one that was added by the compressor. But then to get H1 is at a pressure of 177, which you can get what our liquid, our enthalpy of evaporation here, which is HF. So that means H1, we can then say our H1 it's equals to 460.7 of this one. This is H1 at the pressure of 102. And then when it goes to H number 2, it's outside. But then from 2 to 3, this one is inside. We're looking at this one that is inside here. So the one that is inside, this one is inside this second. No. So the one that is inside is the one that inside the refrigeration system, is the energy that it's on the system. But then the outside is the external one. That's why here we say it's undergoing a refrigeration. That means it's losing the heat energy outside. And then we have also this one, the effect inside. So here, which is H number 3, H number 3 would be given at this pressure of 962. That means H3 here is this 482. Let's say H number 3 is going to be 483.6. Now, so if 843.6 is AOH number 3, then now you can calculate what this one. So H2 and T2 and T3 you can read from this one. So this is your your T3, T2 and T3. So that means 2 is 102, and then this one is 45. But and then the remaining problem now is this CP. So to get CP, then now we can get this CP from the formula of your entropy. So entropy number 1 is equals to entropy number 2, or change in entropy. Yeah. So change in entropy is always S2 minus S1, then CP in ln T number 2 over T1. It's like this. And then you make sure that always when you use the temperatures here, they are in kelvins. And then this one, we can then get this side now of the C. So we can then say the CP is equals to S number 2 and S1 over ln into T2 over T1, right? So then you can get your CP. But then we said this one is always okay from this point. This one is 1 and 2. 1 and 2 is always the same. But to get from this side, you can look at 2 and 3. So this is your initial, this is your final when you're looking at 2 and 3. So your initial is going to be 2. Let's say this is your final, this is your initial, right? So if this is your final, it has to be 3. This one, it has to be 2. We can then convert this one 3 and 2. And then from here, we say that this is your final, it should be 3. This one, it should be 2. Then you can get what? Your CP. So to get your CP now, we need to look at your enthalpy or your entropy. So we say the S1 is the same as S number 2. From the table, S1 is the same as number 2. And then from this table here, your S1 is at 1.7. It's 1.762, and then your S number 3, which is your entropy number 3, is going to give in. This is the entropy. Number 3 here. So entropy number 3 will be given at this pressure number 2. Remember, said the values at pressure number 2 is this one. So the pressure here, number 3, is also at the pressure of 967. So then from this point, you can then say number 3, it's 1.587, which is this one, right? And then from there, you can calculate your CP. So your CP will be substituted by these values, and then we said this is your 1.587 minus by your 1.762 all over ln and your temperatures. So your temperature number 3, it's 45. I'm looking here, your temperature number 3, it's 45. But then this 45, we need to add with what? We need to convert it into kelvins. Then it's going to be like this. And then temperature number 2, here it's 102. Then we need also to convert it to kelvins. Now, and then from there, now you can get your CP. So after finding your CP, then you can put it into your formula here to get what? To get H number 2, because H3 is the one that is on your table, which is this one, 480 483.6, and then now you have your CP, and then you can add this one to get what? H number 2. So then we have now solved what? H1 and H2. So we need what? We need H number 6 now. So to get H number 6 now, we continue looking at this one. So that means from this one we now go, okay, we go to this one now, and then from this point we have to looking at here. So to 4 and 6 we can then get what we can, 4 and 5, sorry, we can then get what? Your 6 here, because 6 is the same as number 4. Okay, so to get H number 5, we can then say it, H number 5 now it's equals to H number 4, because this one are losing heat energy. We say we're going to subtract with CP into T number 5, sorry, yes, 3, and T number 5. It should be like this, right? So now at this point we are looking forward for H5. So this is our H5. This one, we say that this side it's losing, sorry. So we say that this side it's losing, but this side is gaining, because this one was the compressor here, but now this side is what? This side is the condenser. This condenser says it's designed to substitute what? The heat energy, or to release the heat energy from the steam. So it changes into water. So when it changes into water, now the heat energy here, that means this one is your HF, but then this one was from here it was HFG, because it's what? Is the heat energy that it's released by the evaporator, or is the evaporation heat energy, which is called the specific is the enthalpy of evaporation. But then here now, because this one is changing into water, therefore we're going to read what? HF, because it's what? Is the liquid enthalpy, or is liquid enthalpy is the heat energy that comes with what? With water. So when it changes into heat energy, then we can then go to our table again. Our table here at what? At the pressure of, this is the pressure number 2 now. Pressure number 2, looking at here, this is our pressure number 2. We're looking for H number 4. So H number 4 is going to be 133 now. So we can then substitute here, say this is 133.0, which is this HF. Then we can substitute with what? With our CP that we got here, and then from there it's going to be the T2, T3 and T5. So T3 and T5, this one is 45 and 35. So we can then say this is your 45 minus your 35, and then you can get what? Your H6, which is your H5. H5 is the same as what? H number 6. So from there you know that this is what? This is your H number 6. So now you have concluded you got what? These values, both of them. So you have H1 minus H number 6, H2 that we got from this side, minus H1, you will get what? The specific the coefficient of operation, which is your this one is your refrigeration effect, and then this one's the external heat energy. And then yeah, so I think this is the what we have to cover from this one. Okay, but then we also had the other question here at this side. Oh yeah, this one. they said we must also calculate what the mass of flow of the refrigerant with in kg per hour. And the last one, we need to calculate what the refrigeration water required by the condenser, in kg per hour. If the increase in refrigeration water is limited to 12 degrees. So okay, so now the mass of flow, the mass of flow of the refrigerant would be given by the formula of so you can say the mass of flow per hour. The mass of flow per hour would be equals to the volume that is flowing in the system, per hour over the saturated volume. This saturated volume is at the lowest pressure, which is the volume of the water at the lowest pressure, or the volume of the refrigerant at the lowest pressure. And then this one is given by cubic meters per kg. And then this one is also given in cubic meters per hour, like this. And then we can then get what the mass in kg per hour. So remember, we're needing to get the mass. That means this one will cancel, and then we're left with kg per hour, like this. And then remember from the question, now we're given what the coefficient of efficient, the efficient or the volumetric efficiency, which was something like 80 something. Yeah, from this point they said the volumetric efficiency is 80. This is your volumetric efficiency. So we can then say this is 80% of the volumetric efficiency. And then we also had this statement here that says we have this is the speed of the compressor per minute. And then we also have the volume, the volume or the stroke length, and also the diameter of the compressor. This can give us what the volume of the compressor. We can then say the volume of a compressor, now it's equals to an pi d squared over 4 multiplied by the length. And then our length here, it's what our length is 75 together with the diameter. So we can then say that this one is pi times 0.075 squared over 4 multiplied by 0.075, and then we go to the volume. But then this volume that we have here, it's running in what it's running in at a speed of, they say it n, it's what, it's a speed of where is it, where is it? N. Oh, here it's a speed of 300 per minute. So that means here you have 300 ref per minute. Yeah. So this one, it's giving you what, the volume delivered. Okay, so this one is giving you the volume delivered, and then the volume delivered is this one. So from here you can get your volume, and then from your volume, then you can put it into your volumetric efficiency to get the actual volume. Then this one, we know that efficiency is always the output over the input. So this one is the input because it's coming from the compressor, and it's coming from the diameter of the compressor. And then to get the output now is going to be 0.8 of your coefficient of friction multiplied by the answer of this one, which this one is equals to 0.00033, and then you're going to multiply it with here 0.0033, and then from there you got now what the output volume. So this output volume is the volume that is coming with what is the volume that is produced by the compressor, and then from here we can then convert it by our speed. We can then say the speed here multiplied by the volume per hour, right? Because we need this one, this is per minute, we need to get it per hour. So that means our answer here, which is going to be 0.002 or 0.264 multiplied by the speed, which is 300 multiplied by 60, because of what, of this minute. And now we're looking at what, per hour. And then you got your answer from here, and then from here you have you're going to have an answer of 4.752 cubic meters per hour of volume. So this volume is this one here on top. So then you put it here, and then from the table you're going to read at the pressure, at the lowest pressure. The lowest pressure is your pressure number 1, which was 177, and then your VG is going to be 0.233, and then this one divided by this answer here of 4.752 divided by 0.23, you will get your mass per k hour. So that means your answer will be kg per hour. So this is the mass that will be delivered per hour. And then the last one they say you need to calculate the increase, the last one will say you need to calculate the volume or the refrigeration, the refrigerating. Yeah, I have a problem announcing R. Okay, so the refrigerating of the water by the condenser, if there is an increase in the refrigeration water, it's limited to 12 degrees. So if it is now limited into 12 degrees, therefore we need to calculate the mass, and the mass is going to be heat energy of water. You know that the heat energy it's equals to the mass multiplied by specific heat capacity multiplied by the change in temperature. So we know the specific heat capacity of water is always 4.187, and then the change in temperature in this case is our 12, and then we need what? We need this mass, right? This is the one that we need. Therefore now the only problem lies with what? Lies with our heat energy. So the heat energy that it's displaced by the condenser. Now the heat energy that was displaced by the condenser, when you're looking at here, we say the heat energy from the condenser is this side from this one. Now, so the heat energy that will be displaced by the condenser, it will be then be H2 here to H5. So we can then say that this heat energy is equals to H2 minus H5. So, and then we know that H2 is 544 minus our H1 is 116.8. And then now you got what? The heat transfer by what? By the condenser. This is the last one, which is the condenser, right? And then from there you have the heat energy per hour. Remember, we are calculating this water the mass per hour. So this heat energy which is going to be, this one is going to be 427.2 multiplied, this is the answer from this side. And then now to get the heat energy per hour, the heat energy that was transferred per hour is going to be this 427.2 multiplied by the heat energy that flows in the heat energy that flows in the refrigerator. So the heat energy that flows in the refrigerator is equals to, yes, so this heat energy will be equals to, this is the heat energy per hour, will be equals to the mass that we got here, the mass that was flowing per hour, this one multiplied by this H, because now we need what, the heat energy per hour. So this is the heat energy, or you can just put it from this point and then say multiply by the mass that is flowing at this point, so that when you subtract these two and then multiply by the mass, you get what, the heat energy. So it's going to be our heat energy at this point, and then this heat energy divided by these two, you will get your mass that is flowing there. I hope you enjoyed, guys. If you have questions, I know that sometimes the example that we are doing here, they are confusing, or you don't understand them. So you are always free to contact me, maybe on my email if you don't want to WhatsApp. But the WhatsApp, it's the number is 061 4985061. So this is my contact number. You can WhatsApp me so that we can chat and have maybe clarity or ask questions about this, so that we have a better understanding at this such question. But then I'm still going to do at least 4 more examples of this one, so that everyone gets the picture.